Anyway, you'll have to put up with me giving an overview of the Optoelectronic Information Processing portfolio. And basically, we're here to explore, the portfolio explores optoelectronic information processing, integrated photonics, and the various associated optical device components, fabrication, and processes for air and space platforms. And we basically want to impact computing, communications, storage, sensing, and surveillance. And basically, I guess it's not as bright as it was earlier. I guess Kit used up all the power. So, basically, there are 6 area: integrated photonics, nanophotonics, oh, another one, reconfigurable photonics, nanofabrication, quantum computing, and using optical methods and terahertz sources and detectors. One thing I guess I should say that the program is basically very device oriented, but if you're doing devices, you also have to worry about materials, fabrication, simulation, theory, et cetera. I guess I should go back here and focus on the, I guess, the kind of basic research element here, or the exploratory aspects of the program is to basically look at light matter interactions at the sub-wavelength and nanoscale between metals, semiconductors, and insulators. And so there are other, certainly there are lists of scientific challenges, everything from radiative lifetimes and gain dynamics, fundamental building blocks of information processing in the post-CMOS era, and then there are challenges associated with fabricating all of these particular devices. And certainly we're motivated by a thing that or a concept that I've talked about in the past about bringing nano to photonics. And of course, there are other issues, interconnect issues, addressing novel computing and so on. And we certainly are very upbeat about this particular area, that we kind of consider it the engine for 21st century innovation. And lots of payoffs, as to exploiting CMOS, and kind of a DoD component here, being concerned about size, weight, and power type of issues. And there are certainly transformational opportunities here. For example, the reconfigurable photonics component there. If you could have optical FPGAs, compact beam steering. In the terahertz regime here, there are opportunities with looking at bandwidth problems, high-speed wireless communications, non-ionizing radiation sensors, and various types of spectroscopy. Actually, Rick talked about the frequency comb spectrometer, and that kind of came out of terahertz effort that was in a FY03 Air Force OSR Muri. And so that is really a big impact, paper has a really big consequence in the future and some of the things that we're planning to do. And so just kind of wanted to highlight that aspect. And so also as we move into the area of integrated photonic devices, again, there are the swap size, weight, power kind of enhancements that we can get from that particular area, which basically addresses a lot of things that the Air Force is interested in. I'll focus on 4 different areas as to kind of results that come out of those particular components within the program. And first I'll make some more motivational comments here with respect to, I guess, bringing this idea about bringing nanoscience, nanotechnology to photonics. Certainly photonics doesn't really need much motivation here. What is given here is over 2 decades. The number of internet users have gone to about 2 billion, and that basically has been made possible by the development of the laser, where we just celebrated the 50-year anniversary of the laser, and also Nobel Prize was awarded for work that was done in fiber optics. So what we want to do is take this particular technology and impact also the 21st century with making these things faster, smaller, cheaper, and less power. And I guess I should say with the less power that it's extremely difficult to see here, but the IT energy budget now is such that if we look down the road, that by the year 2020, we are basically using all of the power that is generated in the country to run IT-related things, from data storage, to running various types of switches. And so we do have to think about low power and low power, kind of devices, and we hope, to use photonics, for that. And one stumbling block, however, is that photonics deals with photons, which are wave phenomena, and so historically, photonic devices have been actually large. They've been on the orders of the wavelength, so be it micron, 2 microns, 10 microns, and so on. And so how do we, make smaller devices? And one area that you've seen the phenomena that we're going to use is in stained glass and glass goblets and so on, as to the light transmitted versus reflected and so on, that there are these metal nanoparticles in the stained glass. And we're going to use those metal nanoparticles to manipulate light, because those nanoparticles, the plasmon effect, basically can use the plasmon effect, and so we can use these particles to concentrate light, and they can act as antennas at in the order of 1,000 times the field concentration. And so the light couples to the electrons on the surface, here's more of a I guess a wave phenomena of it, but ultimately plasmonics allows us to work in a regime here where the electronics, there are limitations on the speed of electronics, and in the photonics, there were limitations down here in the smaller scale. And so plasmonics basically allows us to work in the smaller regimes. And these are now going to be a series of slides from Harry Atwater's program at Caltech, and he's been a leader in plasmonics. And basically, I'm going to actually go through them rather quickly. That basically this is the objective here, is to design, demonstrate plasmonic nanophotonic materials and structures for CMOS compatible active switching and control of spontaneous emissions. And the key aspect here is being able to manipulate the refractive index for modulation, and then to design ultra-low loss plasmonic materials. AFOSR, we've been kind of leader in the area of integrated plasmonics, or putting plasmonics on chip and so on. But that has been one aspect with plasmonics, is the amount of losses that can occur if you have a waveguide and some of the components on it. And so to do that, we basically have to look again at we basically have to develop ultra low loss plasmonic photonic waveguides, couplers, so that we can operate at much lower than the wavelength of the light that we're dealing with. And so these are kind of test structures that are set up to look at some of the materials where you couple in the light. You have a waveguide here, the PMMA as a waveguide structure leading into a SOI structure, and And so the ring, here basically allows you to couple in and, kind of study as to what the effects, are. And, and then there are, these kind of grading output couplers and so on, that are used. And a lot of that work also has a lot of simulation, work and so on. And so I guess the bottom line here is that it turns out for kind of ideal, coupling, between some of these waveguide structures that are being, examined here is that there needs to be kind of a notch or offset and so on that occurs, between the interface. And this is work actually kind of a modulator for plasmonics from a couple of years ago. And the limitations, there on that particular, modulator, is the index of refraction change, because basically what you're using, for the modulation is, changing the index of refraction. And so, here are some of the numbers here that you can see at 1.5, micron at the telecom, wavelength, is a very small change in the index of refraction. And so what we want to do is maybe explore materials, that where the change of the index is much higher. And so we're looking at some of the conductive oxides. And so this is kind of a test sample here for ITO, and where you can see for different wavelength here as to the change that can possibly occur in the index. And so ultimately, that part of the program is there to also then explore whole kind of a material systems like some of these conductive oxides and some of the semiconductors and so on, as to replace the gold and silver that is currently being used for these devices. A kind of a major or a significant component of the program is the idea of kind of non-periodic complex nanophotonics, and because of the chip scale photonics, we want to look at a lot of the I guess components for wavelength division, multiplexing, and multispectral sensing, for photovoltaics, optical switching, and so on. And so there's a need to develop, these optical structures. And so there's part of this program includes a MURI, program, and so these are, some results from that MURI program. And so the major motivating factor here is that most nanophotonic structures or devices are regular. But in general, there is no intrinsic reason to prefer regular structures. And so what could we do to have irregular structures that kind of guide some of these devices that we want in the future. And so because ultimately we have lots of degrees of freedom to work with some of these structures. And so this one particular example here, we're looking at a WDM filter, design that, again, in the past, the photonic, components were rather large scale, and so what we're trying to do is kind of, pull this down into the, micron, at least the micron, size, and so one of these kind of complex, structures, that we're kind of looking at, is this kind of photonic band gap, structure here, where you're bringing in light here with, multiple wavelengths, and you can basically, by this kind of what appears to be a random kind of structures here, you can pick off, different, wavelengths. And this was basically calculated that way as to input, and you want a particular output, and so there's a lot of mathematics that goes behind it, and so there's a Dirichlet to Neumann approach to the problem, where I guess a lot of the parameter space is basically at the edges of these cells here that you're looking at. And so that particular approach has allowed us to go from calculations that might take days and so on to matter of minutes and so on. Another component there again under this whole area of nano photonics is the idea of low threshold, low power nanolasers. And here are examples of for each one really deserves multiple slides to really go into it. But I mean, these are all really big highlights that have received a lot of press this year. And this particular one with its bottom-up photonic crystal lasers using nano pillars has threshold power densities of 75 watts per square centimeters, and it's the first nanowire or nanopillar-based laser with performance comparable to planar-grown devices. And work out of Stanford here with Jelena Vukovic was to look at some extremely low power consumption devices. Here there's lead selenide quantum dot lasers on silicon out of Michigan, and then some I guess nonlinear generation of light with plasmonics from the Stanford group. Changing now topics here. A couple of years ago we had something called Discovery Challenge thrusts, and we kind of aimed to look at kind of novel electronic materials and nanostructures for kind of real-time dynamical large electrical and optical property tuning. And so we've kind of looked at various properties that basically as to manipulating the electric field, magnetic field, temperature, mechanical stressing, and so on. And certainly one thing that came out is this huge book. It's this thick on kind of spin transport in magnetism. And so there are magnetic efforts. There were memristor kind of components here within this particular program. But it's actually some interesting work that came out of this. And unfortunately, it's kind of elements of it winding down, but trying to continue some aspects of the program. On the optical side or the photonic side, that are kind of looking at photothermal modulation of a silicon vanadium oxide ring resonator here by using the properties of vanadium oxide, that the phase transformation that it goes through from semiconducting to metal, as you change the temperature here, then there is a shift that basically occurs here that allows you then to manipulate kind of switch on and switch off these. And so this is the optical version of it. So previously we used thermally to switch the device, and here by illuminating it with a 532 nanometer laser and so on, we were able to basically change the index of refraction and so switch kind of the component off and on. So we basically varied the electrical, magnetic, and thermal, properties and so on. But a lab component, to this from Wright-Patterson, Air Force Base, we're actually looking at manipulating material, and so this is a kind of, I guess we call it programmable, reconfigurable, sensors. We're kind of smart matter, and so we're actually, producing. These are generated, by the effort in the lab. These less than millimeter, sized, spheres and so on that you ultimately can kind of reassemble into, let's say, some kind of a sensor, aperture and so on. So AFRL will be the first to integrate these structures and program, them. And I've basically coupled them into the program with some of the flexible, electronics, that we've been using, like some of the nanomembrane, work, and also the way we've been trying to enhance the program is through STTR that we actually just, over the last day or so, the contract has been let, where they're going to work with this a small, company, to implement, some of their, concepts. Trying to make, these, spheres and so on that have a certain amount of functionality. Okay, so, as I kind of indicated that, a program like this, for some of these really neat, devices, you need to address, the fabrication and kind of, neat kind of materials. And so, a couple of years ago, we went into this area called membranes. And so manipulating these membranes and what can you do with these? Because, when you put these, besides the basic science of trying to understand nanomembranes as to how, how they fold, how thick they are, how you process them, and so on, they lead to, because they're all single crystal, they're on single crystal, background substrate, all of the devices that you produce on these are, have excellent, properties. And so if you can, stack these and so on, that you can generate some of these optical phased arrays and some true time delay, type of devices. And so Ray Chen from University of, Texas here, you can kind of see, this schematic, here where, we can see, stacking, these nanomembranes, with various functions, on them. And, to be able to do that, you also have to have a certain, fabrication, capability. And so he's teaming, as one of the Muri team members is at the University of, Illinois, and so they have kind of a machine vision robotic, system that allows, that, to happen. And so there's this whole, process as to exactly how do you, these flexible, kind of small, extremely small, structures, how do you, stack them, on top of each other and process, them. And actually, so some of these some of these nanomembranes were actually manipulated with this system when we had a program review back in October and so on, that if we basically put I guess it was actually the other one here. There's out of these nanomembranes, it's actually printed here on this particular slide, and so these are just, they take the membranes, and it's very, of course, automated and so on, and print out all kinds of, structures. There's actually also a kind of a inkjet, approach. What they call it, electrohydrodynamic, ink. And so there's another one that I have here with the Air Force OSR logo, which is done with certain polymer, kind of one micron size, droplets and so on. So there are all kinds of things, and there's actually interest now. We had a team going over from RY, to the University of Illinois, and they want to start a LRIR, effort in that area. And so kind of besides the kind of what appears kind of a practical, approach, to it, to that area, there's also just kind of the basic understanding as to how these materials, work, and so you have these stamping systems, that operate, that are on the order of, tens of microns down to micron, kind of size, and how do they adhere, to the surfaces, you have to worry about how you pull them off, and because ultimately you need to, pick up things and then place them, and how do you pick them up, and how do you place them, how do you, remove the stamp and so on, and so there is a, certain amount of, work in trying to understand some of the basic, properties and basic, basically the basic understanding, of all of this. Nanomembranes, there are a lot of things in the optical regime, from For some, because of the size that you want, you need kind of a frame to assist, the structure, though it stays somewhat, stable, and there are also things in electrodes and photodetectors and solar cells, work that has been done there. From STTR, kind of a tech transfer that has occurred, from that particular, the nanomembrane effort that we are currently first to demonstrate optically pumped lasers on silicon based on nanomembrane transfer, printing, and so you have a VCSEL, structure here that uses these nanomembranes as a, where the nanomembrane is this phanomembrane reflector and so on, and that's the key element, here, and so you're able to make this VCSEL from these kind of stacked devices, and so it gets around a lot of the problems that people have with generating kind of compact VCSEL structures. And then finally, in the area of nanomanufacturing, another STTR effort actually that was kind of was an opportunity through OSD to fund some developments in the area of fabrication, nanofabrication for photonic applications, where there's this zone plate array lithography, and we're kind of focused in trying to make 3D structures, because ultimately, again, you want to basically move in that particular direction, 3D electronics, 3D photonics, and so on. And they've demonstrated with their I guess zone plate array lithography, with these these extremely small zone plates here. They've been able to create this array of ring resonator filters coupled to a waveguide, and so we're waiting to see what could perhaps happen in a phase 2. As indicated at the beginning, I look at issues associated with quantum computing from a photonic perspective, and there are basically about 5 efforts in this area, and one at Northwestern is kind of an atomic assemblage of qubits, and Duncan Steele, he's looking at coupled single electron doped quantum dots. There are model-oriented things associated with microresonator circuits, kind of the diamond nanophotonics, approach, like Kit was talking about, the NV, diamond, and then Leuenberger, who's basically kind of a theoretical approach, kind of a quantum network inside a photonic crystal made of, quantum dots. And so, we have all this device work, but with that, there's also a certain amount of theory, as indicated before, simulations, modeling, and also a lot of theory, development. And and so the attempt here was to fully understand, the spontaneous emission of a photon, from a quantum dot, structure. And so, he came up with, for this particular Lagrangian, to use this modified tensor to, address, the system. And so ultimately, what that allows, the work that he has done, it basically allows you to have a kind of a 3D visualization of the emitted, single photon field, and using these isosurfaces. And so for that particular work, basically it's led to kind of understanding as to the kind of the decay phenomena here, that it's a rather low order polynomial decay, versus exponential, decay, and there are high frequency near field oscillations, that are visible. And so he's going to be coupling or collaborating with our PCASE star, Dirk England at Columbia University, and actually Bob Bonneau, he has some efforts there also with Dirk, just like the people at Rome. So Actually, I guess in conversations with our EORT, partners, I guess I certainly encourage that some of the efforts that we're supporting now with, I guess, at the University of Bristol, maybe to start interacting also with Dirk. Okay, so my programs had, I guess, the opportunity, I guess probably because it's very device-oriented, lots of transitions, and lots of things, not only through STTRs, but other mechanisms. A really good transition has been the development of a terahertz detector, and we're, the tracer diagnostics here with working with AFRL and the state of Ohio. They were able to, get $3 million of funding from Ohio and another $1 million from AFRL, and so they have developed now a terahertz detector, and actually they're trying to come out to show it to me. And EM Photonics, through phase 1 and phase 2 activities, in the area of kind of chip scale routing in architectures, they've basically been able now to transition their WDM router to the F-35 and some satellite optical backplane work at Kirtland. And something that's really been in the news, I guess received a lot of attention here recently is this plasmonic cavity spectroscopic polarimeter. And this kind of a chip scale, a detector or polarimeter that basically has the full Stokes vectors that it can basically pick up. And the key to look at, and I know it's kind of difficult, from the back as such, but there are 4 in this pixel here. There are 4 different structures here. There's circular, one, and this grading structure and this grading structure all kind of orient differently, such that you're able to pick up the 4 Stokes vectors, and basically the radiation essentially gets picked up and is brought down to photodiodes here, and these structures have extremely high extinction ratio, and where they actually predict from simulation, they predict extremely high extinction ratios. But anyway, here's our attempt to actually integrate these on a focal plane array, and so there's a very kind of compact polarimeter device. Interesting has also been the work out of the nanomembrane work. That's a huge effort now at NIH in being able to detect protein masses. And again, this directly outcome of the nanomembrane in Muri, and which was kind of a surprise, for it's kind of a, I guess, well, I forgot the terminology, something in flight, anyway, that's been basically developed over the last 6 months, that particular transfer. University of Delaware, they're really close working relationship with RY and RX, and so they're able to land this conformal shared apertures for Air Force, platforms, kind of bringing metamaterials, to various RF photonic systems. And then I guess I should say we also transfer, I guess, a tech transfer of people. And so we have another SMART program participant. And this effort here from Terahertz Device Corporation that has resulted now kind of in production of various LEDs and so on is actually an effort from 2001. And that over time, they have kind of found their way from work that they originally did in the area of terahertz, actually looking at photonic crystals and terahertz, which has led, to work not only in these being able to offer LEDs as a product line, but also work in the area of trying to look at BIWO, product for high terahertz, sources. And so the photonic crystal, this can probably be skipped, as such, but photonic crystal work basically impacted, these the BIWO work and some of these other things in their product line. This whole idea of slow wave circuits was impacted by that work. So that's always a challenge. Is for something that that maybe a decade ago, where did it go? And out of the blue, he contacted me to let me know, about that that particular development. Kind of interactions, with the various other on that we time permitting, and we try to interact with the DITRA and JIDO on the terahertz front. Quantum computing, and Tatiana is involved in the NSTC subpanel and on QIS, and so we kind of get involved in sharing information with the other agencies as to what we're doing in this particular area. I guess Air Force OSRs within the government has been somewhat unique as to what we've been doing in reconfigurable photonics and electronics, and probably have had kind of the major effort. Nanophotonics, I think we're still kind of the leader, within the DoD, of course. NSF, has programs and so on. So, but certainly a lot of things that we have done in this area has kind of driven this particular community. Certainly, when it comes to integrated, photonics, the big players like DARPA and NSF, have programs and so on. But again, I think there are certain areas that we've kind of focused on, like silicon photonics and the plasmonics, and even some of the work that goes back almost 2 decades with what we've done in VCSELs and so on. We continue to to lead in those areas. So again, plasmonics has really been kind of a star within our particular program, and lots of people have there are lots of programs have kind of evolved out of those areas, from energy to chip scale kind of components, and so we continue to be leaders there in the whole area of nanophotonics and nanoelectronics, and engaged through our position within the National Nanotechnology Initiative. We do engage with other agencies and so on. We have lots of bright people that get a lot of awards from basically John Rogers, who continues to get these awards, getting the Oscar for Inventors, the Lemelson MIT Prize, to Dirk Englund, Harry Atwater, Jack Ma, and Jennifer Dione. Still hoping that she will be a next PCASE winner. Finally, besides interacting with other agencies, we also interact, of course, within here Air Force OSR, the various individuals here, and across AFRL. I guess within my program, primarily my interactions have been with these first 4 here, RY, RI, RX. And here's a kind of a sense here as to what we're, which way we're going here. And yeah, so continue to emphasize kind of nanophotonics and also integrated photonics. And guess I kind of wind it up here, and just it's kind of sad to I guess I should have really had that on the top here, that Professor John Caulfield, he just recently passed away, and he was kind of a leader in the whole area of optics and photonics. And these are some very nice pictures from a effort with Oliver Schmidt in Dresden, Germany, or they're using rolled up nanomembranes, and there are all kinds of more biological, type of applications, there. So this is my last slide. So I hope that you get the idea, or at least I hope the key ideas that you come away with, is there are lots of things going on in the program, and key ideas here within the program are plasmonics, bandgap engineering, strain engineering, refractive index engineering, metasurfaces, et cetera. And finally, again, that integrated, photonics has a big impact in this whole area of the swap, size, weight, power, and can bring a lot of increased functionality to components. And a major aspect of it, however, that has been missing is a kind of a process, a shuttle process like MOSIS for photonics. And so there's a program that we have with Professor Michael Hochberg, who was at the University of Washington, now transitioned to University of Delaware, and he has a program called OPSIS. And if you want to know more about it, I have pamphlets here that I'm willing to hand out on that particular program. Thank you very much.
Thank you.